Okay, so everyone can hear me? All right, so thank you. Okay, so now let us continue back with the sorting. Okay, in case the first session, we have the bubble sorts and also the insertion sort. Right. Okay, so now we go to the merge sort. So for merge sort, basically it's about divide and also the conquer. So what does it mean by divide and also the conquer? Is we try to divide the array into half. So how does it actually divide? It's actually divided until it cannot be divided anymore. So once it cannot be divided anymore, it will start to combine. If we look at this one, so this one basically is actually looking like a tree that we have actually gone through in the second workshop, where it looks like the tree. So let's say this one, 8375. That how are you going to sort it out? So first thing, 8375, sorry. So we divide it into 83 and 75. So after that, further divide it, 83 and 75. So once we reach the stage at 8375, which means that cannot be divided anymore, right? Then what we do is we combine them. But during when we combine, we will do the sorting when we actually going back. So let's say here, 83, okay, combine into the sorted array where it will become 38. Same for 75. It will go back and become 57. Then later, it goes back that combine 3857, it will be 3578. So this is how the divide conquer works. So let's say we take a longer examples that we have these array, set of arrays 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. So each set that we think of this as we have 11 elements and we have divided into 2, which is half. So now we try to combine between these 2, which is A and B. So before we go into the A and B and try to combine it, we're going to have a temporary array to actually store the values of the combine. So now let's say, first thing, it will compare 3 and also 6 to see which one is larger. So here, 3 and 6. So of course, we're going to choose the smallest one and place it in the tab. It would be 3. Okay. Then we go to the next one. So in A, we have put the 3 inside, right? Then we're going to look into the J and we're going to jump into where we're going to increase the values of I to be 1. Combine it, J and combine J equals 0 and I equals 1. Combine 5 and 6. We try to compare which one is larger. Obviously, it is 5. Then later, again, update the values of I. You have to jump into another index and look at, okay, compare which one would be the smallest. 15, compare with 6. 15 would be smallest, and 6 will be smallest, sorry, 6 will be smallest. Then we're going to put it into the tab. So here, this one will continue again and again. So 15, if compare to 10s, then 10 would be the smallest. So we're going to put 10 into the temporary array. Then it goes to the 14. And you're going to place 14 because 14 compared with 15, 14 is still the smallest. And then we go to 15 and 22. So this round, of course, 15 is the smallest. Then we're going to put into the temporary array. Then it goes on and on, 28 and 22. So it would be 22. Then 43, okay, and compare with 28, then 43 with 30. So this one, A is done. And of course, we're left with 43 and 50. So but what happened is that done, okay, no more elements. Then it would be 43 and 50. So what happened here is Y is 43 that we put it in. Remember that when you combine, okay, you combine between the trees. So if let's say we go back. So if we look at this tree, is, let's say just now, this is A and this is B. So when it's actually combining, it's already been sorted. Okay, it's already been sorted. So here, when we start to combine, it's already sorted already. So when you're actually reaching the 43 and also 50, definitely we know that it's already sorted. So we don't need to check again, go through and sort it again. So this is what happened. Here we need a temporary array to carry out the sorted array. Then we're going to replace it back. When we look at the pseudocodes, okay, so when you look at the pseudocodes, it will actually divide it into a few functions. But first thing is, we have to check whether the size of the array is it greater than 1. So yes, then we have to split it into the first part and also the second part. If you see with the patterns, so basically the patterns that we're going to use is the recursive functions that already discussed in second workshops. It's about the recursive, where you're going to keep calling the same functions again and again. Then you're going to backtrack after you have completed the whole functions. So here is you split, and then you have the array. So this array is the elements or the items that we're going to pass in, and we're going to split it into the first part and the second part. After that, we're going to sort the first part and also first part, and then later we go into the second part. If you go into the sorts or the split function itself, it's going to be a recursive one. So after you have sort out the first part and the second part, then you will combine the first part and also the second part. So nothing will be done if it is sorted. If it's sorted, means that you don't need to go into and split and then combine, no. So if we go into, okay, the pseudocodes. So for this one, okay, basically it is actually the M sort 2. So M sort 2 is you're trying to perform the sortings when you actually track backs. So here we have this, where you're going to pass in the array and the size. So what is the size of the array and also the temporaries. So how are you going to do the sorting? Here, same thing, okay, check back whether the size is actually greater than 1. Okay, in here, M sort 2 is array. Okay, tackle the first half, where we're going to look at just now. Remember that previous we have the sorting, where we need to look into the first parts of the array, and then we look into the second part of the array. So after we look into them, then we have to merge the whole array together. So here, first parts is always the size of the array that we're going to divide it into 2. Okay, then the second part, it would be meet. Size will minus with the meet. So that one, I will show you later that how it is actually work, but probably it's a bit it will be a little bit confusing because there's a lot of things that we need to look into in the merge sorts here. So this is basically how is going to look like. So when we do the merging, when we do the merging, because after we actually sorted out itself right here, that we need to merge. So for the merge here, what we need to check is we need to check with the size of the k. K equals 0 basically is actually representing the size of the combine the merge itself. So here, k equals 0. You can see here the size of the A and plus the size of B. Here we have 5 and here we have 6. So which means plus in that we need to go through 11 of the iterations. Then, so you have a few conditions that we need to look at. So let's say, if I is equals to the A size, where A is running out of elements, so which means that temporary K will be equals to Bj. So which means that you just, because let's say A here we done, then we just copy back what is the J, what is actually in the J. Then else if J is equals to B size, which means that the B here is actually running out of, it's already done already, it's already been in, which means that the elements here is already been merged into the temporary array, then we will have to copy back the elements of A into the temporary array. So for normal case, which is we combine the, not to say combine, but we're trying to compare the elements of A and also the elements of B. So the elements of B, A and B, so like this one, if 3 is less than 6. So here you can see that temporary elements of K will be equals to A1, so which is this one. So it's actually trying to check whether who is smaller. Else means that if the B is smaller than the A. Okay, for example, like if let's say when it comes to 22, it's actually smaller than 28, then we will get the elements of the B and put it into the temporary array. So this is how that the merge works. So all is actually recursive. Is actually we need to use the recursive functions to call another function. So like this one is first thing we will try to create a temporary array, which is actually using the pointer. So if let's say the temporary pointer is actually null, which is a special case, means that we don't have enough memory to sort out the list. So then we call the M2 sorts. So M2 sorts means that if you still remember, I've shown it to you that M2 sorts, how does it actually look like? That we're going to pass in all, separate the array into 2 parts, and then we're going to combine them after perform the sorting for each of the parts here. So like this one, if we look at the analysis of this part, it would be OM. Because this is one for loop, which means that it's go to each of the array elements for one time. So it would be the OM. If we look at the merge sorts, we look at the merge sorts. So here we only go through the algorithms for one time. There is no for loops, there's no while loops, which means that we're not going through every, we're not going to iterations, no looping, so it is O1. So it is O1. But when it comes to M sort 2, all M sort 2 is also the same thing because it's generated using a tree structures of a balanced tree, binary tree. Then, so this one, you see that merging at each level is OM. Level by level is actually OM. And each level, we are actually talking about the log n levels. So that's why it only takes O n log n levels. Whether is it a best case, worst case, and everything, it takes only O n log n. But for the merge sorts analysis, this will actually take more space than other sorts because you need to, because you can see that there's a lot of branches that we're going to create, right? As it's actually working on the tree structure. So it has a lot of branches. Hence, it's actually taking more space if compared to the other sorts, because if you're looking back, the insertion sort or the buffer sort is only using the array itself. But just the problem is that it's going through for loops, a lot of for loops in it. It just doesn't expand its memory space. But here for merge sorts, even though it's actually working on the O n log n, but it's actually expanding according to tree structure. So that's why it needs to use more space than the other sorts. Okay, so now we look into, before we go into the quick sorts, okay, now let us look at this. So this is the code. First thing I'll introduce to you, the very simple ones, that we're going to have the merge sorts that's shown to you just now. And then we're going to have M sort 2, where we're going to do the sorting. And then we're going to have the merge sorts, where we're going to merge two arrays together. Okay, same that we're going to use the size of the 6. Okay, example, same examples, bubble sorts and also the insertion sort. And then here we're going to call out the merge sorts. Okay, before we go into, let us look at a very quick one. If we go into the merge sorts, first thing we have to create a temporary array here using the pointer. Then we go into the M sort 2. So from the M sort 2 here, you can see the explanations is that if it's normal case, we're going to call the recursive functions to process the array. So if we go into the M sort 2 here, first thing, you need to divide your array into 2 parts. So if size is greater than 1, then we go into the M sort 2 again. Okay, why we need to go into the M sort 2 again is because if we look at the tree structures over here, because so in this one, in the first time when you go into the M sort 2, when you go into M sort 2, you divide it into half. So this is the half part. But still, okay, the size of the array is greater than 1, right? Because in here we have 2 elements, which means that it's greater than 1. We will further divide it to become, let's say here, 8 and 3. So here is 7 and 5. So once it is actually the size here, it's 1 already. So which means that it's not greater than 1. Then you will go back and perform the merge. So this is how the algorithm works right here. So that's why it will keep splitting until it's not able to split anymore. So first half, which here, so let us consider this one would be the first half and this would be the second half. So when it comes down here, of course, this one, we also consider first half and also the second half. So once, okay, it cannot be divided anymore. So it will go back and call the merge function. So that's why you have this first half and second half. Then you perform the merge. So we will come to the merge one, just as explained to you, okay, just now, where it's going to be compare. So it actually depends on the size of the A plus B. So if let's say if it cannot be done, so it comes up here, and it's try to merge, that you actually need to sort it. So the size of the array, okay, it's going to be 2. So this is going to 1 plus 1, then it's going to be 2. Okay, so now we go into the details. Okay, first thing is the size is actually 6. I hope you can follow because it's going to be the things is going to be all around because we have too many functions. Okay, so now you'll print out the elements in the array first. Okay, done. So you can see that it's actually print out the elements of array 22, 78, 59, 56, and 23 and 28. Then we go into the merge sort. So when it goes into the merge sort, it has it is actually pointing back into the array because it's actually passing as a reference. And it also has another temporary array. Okay, so this is a temporary array where it's actually created using the pointer. So normally when we are actually using pointers, the variables that is actually will place it into the heap memories. Then it checks whether is it enough memory or not, because sometimes it's possible that if the size of the arrays that you're trying to work on is too large, and it's possible that the memories is not enough. So of course we have to check. Here we don't have any problems. Then we'll proceed to the msort2. Okay, so we go to the msort2. When it comes to msort2, we will work on this where we're going to decide where it's going to split. So here we have 6. 1, 2, 3, 4, 5, 6. So the place that we're going to split is 3, because it is based on the size divided by 2, right? Size is actually 6 divided by 2 means that it's actually 3. So our meet, okay, the index to actually split will be depends on here. So which means that the first part, it is this part, 32, 78, and 59, and second part would be 56, 23, and 28 here. So check on the base case to see whether the size is greater than 1. Yes, it's greater than 1. So now, follow slowly that we're going to go into the first half. So first half is this part. Okay, so first half is this part. Okay, this part would be our second part. Now we go into the first half. Okay, when we go into the first half, another merge sort2 is created. Okay, another merge sort2 is created. So what happened? You can see that the arrow now is pointing. Okay, we also, because we are bringing in the temporary arrays again, because we have to put it in, right? Okay, so again, now we are in the second, so we are in the first half. Okay, we are in the first half here. And we need to check again, the first half, is it the size greater than 1? Yes. So it's greater than 1. What happened? Same thing, we'll tackle the first half. So what is the first half? We also need to look into the size. So this one, 3 divided, okay, we look into the size here, the middle one is 1, so which means that this will be our middle. Okay, this will be middle. Is it can further split? Yes, it can further split again. So what happened? It will go into the msort2 and split again. So you can see here, we have another msort2. So it's actually further splitting. So for this time, it goes into the msort2 again, and we will check on the size. Okay, the mids will be equal to size divided by 2. So now we look at what is the size. Now it's actually 0 when we further split. So 0, okay, if we check on the conditions here, is it greater than 1? No, it's not greater than 1. If it is not greater than 1, so which means that we have to reverse back. Okay, we have to reverse back. So it's going to reverse back. Okay, now it's actually reversing back. You can see here it's actually reversing back. Okay, when it's actually reversing back, it's going into the second half. So which means that in here, we're going back into this, and this will be the second half. 78 and 59 would be the second half. So we have to go into the second half. Again, okay, in the second half, we have to go into the M sort 2. So you can see here, another M sort 2 is being created. So this is a recursive where it's going to check, is it the size greater than 1? Okay, no, its size is not greater than 1, right? Because 1 is not greater than 1. So it goes back. Okay, it goes back. And what happens is going to start to look into it. Okay, so let us see here. So it comes back here that you're going to start to perform. So it's actually tracking back. It's actually tracking back. So what happened? Okay, it's going to check that again and again. So what happened now is coming back. Okay, now we are actually looking into the second half. So we're looking into the second half. What happened is that we're going to merge 78 and also 53. It's going to merge 78 and also 53. Then now it's going to check. Okay, it checks over here to see whether I is equal to 0 and A is equal to size. So obviously, okay, it's going to be this one where 78 and 59 is going to compare between these two, because now we're actually in the already in the second parts of here. So if it is, then it will start to perform the sorting. So it will be 59 and 78 in the temporary array. So once the merging is done, okay, what happened? It would go back here. Okay, it's go back here, then it would copy the 59 and 78 into the array. So this is the first part that we have sorted. Okay, the first part we have sorted. So just now you can see that in the parts where it's trying to perform the sorts, because in this first part itself, it's actually divided into 3 parts. In 2 parts, where 32, 59, and 78. So 32, because it's itself, so you don't need to sort, but 59 and 78, yes, it will need to sort itself. So now once this first part is done, it's done with the sorting at 32, 59, and 78 done. Then what happened? It will track back. Okay, it track back. So it performed the sorts. So you go up to another level, it goes to 32, 59, and 78. So we go up, you can see that it's actually trying to merge between 32, 59, and 78. So copy back this 32, 59, and 78 back into the original array here. So this would be the first part. So once this is done, with the first part of the array itself. So this is already done sorting. Next, we go into the second part, which is this part, 56, 23, and 28 here. Because it's a recursive, so we have to track back. So you can see that it's actually continue back, okay, going into the second part, and it will start to check same thing. Where is it size greater than 1? Yes, the size is greater than 1. Go in, okay, tackle on the first part. Same thing also, okay, see that whether, we have the mix value similar, okay, similar to the last iterations, okay. So it's actually checking whether is it sorting is actually required, is it already that we need to further split or not. So then here, so it's actually keep going. You can see that now probably we are in the second part. So second part we have to go into again. Okay, it's in the second part here. Okay, so now then it comes here. Probably you'll be feeling confusing, but we can look at the arrows here. Is now it's between 23 and 28. So what is actually happening is that it's trying to combine, merge between 23 and 28. So 23 and 28, that is actually sorting. Okay, so after done, okay, now it will copy back 23 and 28. Then now what happened is it's going to backtrack, okay, to 56 and 23 and 28. So it checks, okay, combine between 56, 23, and 28. So it's actually performing the sorting. So you can see here that it's going to change 23, 28, and 56. So once this is done, okay, it goes back, copy back 56, 23, 28, and 56. So you can see here. Okay, now this is done with the first part, okay, and the second part. So if we compare back to the tree, yeah, okay, so here, just imagine, okay, you just imagine yourself that 32, 53, 78 is now in this stage. 23, 28, and 56 is now in this stage. So each of these states, when it's actually returning back, when it's actually merged, is already sorted. So now what is going to happen is we are already at this level. So we're going to combine back. Same thing, recursive, okay, using the recursive functions that you're calling it. So it's done with the second half. And it's time to actually combine. So when it's actually combined, similar to the explanations here, that it's trying to compare, okay, which one would be the largest, which one would be the smallest, and place it into the temporary array. Okay, so if we look at, okay, you can see that the arrow is actually pointing into, so which means that this is actually the first half and this is actually the second half. Okay, so now 32, if we compare with 23, so 23 it would be the smallest, so it's put it over here. Okay, then go to the next one, which is 32 compare with 28. So 28 would be in the second place. Then 32 and 56. So obviously 32, okay, it is the smallest compared to 56. So that's why 32 is down here. Okay, then, okay, it's actually now checking out. I'm not going to show you one by one. So click on, if you have time, you can click on this things one by one to go through each of the lines. So now it's 32 with 56. Okay, sorry, it's 59 and 56. So here 56. Then after done, so which means that this is done already. So when this is done, then it's left with the first part, which is 59 and 78. So if we go down, okay, you can see that 59 and 78 is. So this is how that is actually sorted. And currently this array is a temporary array. So what happened is that once this is done, it will need to copy back into the original array itself. So you can see here, it starts to copy back 23, 28, then 32, 56, 59, and then 78 here. So once it is done with a copy back, so what happens is that it's going to delete this temporary array. Okay, so once it's actually deleted, Okay, sorry that there's no delete, something is actually happening. So once it's delete, that this array temporarily will be removed, then we only remains with the array that has been sorted here. So this is how the merge sort is actually working, where you try to split it into deep as possible until it's not able to split again. Then you start to combine. So when you start to combine, you will start to perform the sorting. It has a lot of level. If let's say you have a lot of data, then you have to split into a lot of levels, and that will probably consume a lot of memory space. So this is the merge sort. So next, if we look into the quick sort. Okay, so when it comes to the quick sorts, how does the quick sorts work? Quick sort is basically also similar to divide and conquer, that it's going to split. But how does it actually split? It will also split into two parts. It's just that we are not going to, like just now, okay, in the merge sorts, you just divide the size of array in two and you divide it into two parts, right? But here, how does it actually divide into two parts? It's based on an element which is called pivot. Here, let's say in the array itself, I pick one of the elements. Any elements? Yes, any elements. It depends on how you want to pick the elements. You want to either divide into two, okay, you divide into and you pick that element, or you want to get the you want to find through every single of the elements, then you pick the one, or random pick is also depends on how you want to design your algorithm. So let's say here, okay, I don't care how you pick, we just pick one element, and then we're going to partition the array according to the P. So this is a P. The one that is less than the P, we put it into the left, the values. Okay, and the one that is less than the X, which is the P is smaller than the X, then we put it into the right. Okay, so what happened is this is a block and this is another block, right? So in here, you have sorted out, you have put it into two partitions, right? Same thing also. You further from this block, also same thing, you pick a P element and then you divide into two partitions. So let's say here, the example is 15. This is the one that I select. So what happens? Okay, I have to divide it into two partitions, right? That I just split them. So if we check 5, 89, 33, so we'll see that the one that is actually in the gray color, we will put it into the left because 7, 14, 5, and 13, this one is less than 15. But the one red, highlighted with red, is greater than the 15, so we put it into the right. Regroup them, okay, in the left or right. So these two partitions that we are looking into. Then we need to check, okay, this 15 is actually in the index 4. So the actual process is we have to pick a pivot, then swap, and I mean, this is the first step that you swap, put the pivot in the first element. So this is our goal that we want to achieve. Now we start the partitioning process. So here, this is index 0, so K is 1. So advance K to the right and color node accordingly. So 15 and 89, it compares. So 89 is actually greater than 15, right? So what happened is still remain at the right-hand side. 35 is also the same thing, remain at the right-hand side. But then when it comes to 14, so 14 is actually less than 15. So what happened? Okay, swap to maintain smaller okay, elements on the left. So how does it actually swap? So this is the next ones, right? It's actually swapping, something like this. Then we go to 24. Okay, remember, so here this one, 14, so you swap. Then we go to 24. So 24 compared to 15 is greater, so it's remain in the left. Now 5. So 5 is less than 15. So what happened? You're going to swap with the index 2. So swap that you get 14, 5, 89, 24, and 35. So this one will remain. And then 13, of course, is going to swap with 89, right? Then 89 will come over here. So 20 will remain. And then, so this is the one that we get. Okay, at the end, when you do the swapping and try to group it, so this is the one that we get. Then later, you can see here, okay, the second part, everything here is greater than 15. So the last part is we need to put the pivots into the appropriate positions where you're going to change because the pivots here initially that we decided into index 4, right? So we're going to put the pivot back into index 4 and change the positions with the elements in the index 4. So what you can see here, 7, 14, 5, and 13, this one is actually less than 15. So now the pivot is in the correct positions. What happened is same thing, okay? This is the first part and the second part. Repeat that here, okay? You select the pivots again. So when you select the pivots again, then you do the sorting. Again, that you're going to put the one that is actually less than. So let's say here, if you select 14, or we select 13. So which means that the one is greater than the 13, you put it into the right, so which is 14. Then the one that is actually in the less than 13 will put in the left. So this one will continue until, okay, until the one that you are unable to divide it anymore. So first part and second part is actually basically the same thing. So now if you look at the codes that how it's actually work. So this is the functions quick sorts. And we have to check, okay, whether the size is greater than 1 or not, similar to the merge sort, because we need to know whether is it necessary to perform the sorting, is it going to, we need to partition it or not. So if yes, which means that you can actually further perform the sorting. So index is equal to partitions array size, where you're going to perform the partitions. So once you're done, okay, you split it into the partitions, then you're going to do the quick sort. And you can see here, this is also recursive, where it's going to call back until the size of the array is not greater than 1. So it also has the second part and also the first part and also the second part. Similar because it is actually working on divide and conquer. So here, okay, so now let's say we perform, we take the examples here. So step 1 is actually dividing. Okay, meets that size is actually dividing into 2. So the methods that we use here, for example, is we are trying to decide on the pivots where the size of array is divided into 2. So after that, you perform the swapping, because you have, in the first step, you need to swap the pivots into the first index. Then based on that, okay, you get in the k equals the size where you need to perform the swappings. So here when it comes in, okay, we have to check whether either you go to the left or to the right. If it is greater than, if array, okay, it is less than, okay, less than the pivots, then you have to perform the swapping, that you need to swap it to the left-hand side. So for time analysis, so how does the time analysis actually work is, so this is the functions where you call the quick sorts, right? And it doesn't have the for loops. So it's basically it's actually the Q1. But when it comes into the partitions, here we have to look into. So it has the for loops. It has one loop, so hence it's almost like O N. So these are three structures that's actually generated. Most work is done is the partitions. So partition here, okay, same thing because it's a level, similar to the merge sort. So each level is O N. And in each level is a log n level. So what happened is that it can take O(n) log n or O(n) squared. So O(n) squared basically it's actually the worst case. So worst case means what? So if let's say the pivots that you pick is the largest or the smallest, then you have to split it many times, and then you have to perform the sortings and also many partitions here. It can happen, right? Because let's say the pivots that you pick unlikely that it's actually the largest or it's actually the smallest. It means that you have to check through every single of the elements. So that's why in the worst case you get O(n) squared over here. So before we go into the comparisons, so let me show you. Okay, but for this one, probably it's a bit confusing because there's a lot of things which is actually similar to the merge sort. Okay, so hopefully we are able to visualize it. Okay, so this one, similar, we're going to use the example 32, 78, 59, 56, 23, and also 28 here. Okay, that, so we go into, okay, we have that, and we're going to print out the elements of the array. Okay, it's printed out, 32, 78, 59, 56, 23, and also 28 here. Then we go into the quick sort. So quick sort here, check, okay, we have an index. So if the size is actually less than 1, which means that when you're actually reaching the stage where it's unable to partition it anymore, then we will return. So here the size is actually 6, which means that it's not. That you go into the partitioning. Okay, you go into the partitionings where you're going to pass in the arrays and also the size. So now if you come to the partitions where it's going to further perform the partitions here. So the partitions. Okay, first thing is we select the pivots. So pivots based on the mid, it will be equal to size divided by 2. Size here is actually 6. Divided by 2 means that it's actually 3, right? So which means that this will be the pivots, which is the values of 56. So we will do the swapping. Remember that in the first step that we will swap the values of pivots into the first elements of the array. So these two will be swapped. You can see 56 and that 32. Right, so now we go back and then, okay, partition array into 2 unsorted parts. So item set positions 1 to index smaller than array 0. So This one is that you start to move. The one that is actually less than 56, you're going to move it to the right, and the one that is actually larger than 56, you remain at the right-hand side. So what you can see here, you can see the changes are, suppose 32, 23, and 28, it will actually slowly move to the left-hand side. So you can see that now is actually moving, swapping. Okay, so here, okay, it's actually swapping. So it's done. Okay, it's done with the moving. No, so it's actually swapping. So now it's actually done with the swapping. Actually done with the swap here. So what happens? You can see that swap meets with the first item again to complete the process. So it's actually going back. Okay, you swap back the pivot's value back into where it is actually set. Here you have 38, 32, 23. So this is the pivots, which is 56, 59, and 78. Okay, so once it's done, so this is the first quick sorts. Then now we go into the second part. So when it goes into the second part, what happened is same thing. Okay, go into the first part, where here you have to perform the partitions where you can divide this first part. So you can see here that this is actually basically the pivot's value. Okay, you can slowly see the changes where it's actually in the second part. So I'll quickly just click next and go into the, so that you see. So you can see that it's actually keep going into the, it's actually doing the same thing. So if you want to know what is actually happening, so probably have to go into the code itself, slowly one by one. Okay, you have to go into itself and to do it slowly one by one. Okay, and then, so it's actually start to perform the sorting. So it's actually a lot of steps that you do. So what happened now? Okay, it's done. So over everything here, okay, it's just going to keep repeating. Okay, you're just going to keep repeating. So just going to keep repeating everything. So just going to keep repeating until everything is actually done. So this is how the quick sort works. So if you look at the comparisons between the, of course, there's a lot of other sorting as well, but basically all the sorts is actually same thing, where you're just trying to arrange the items into the proper orders, whether it's ascending or descending orders. So now if we look at these four sorting, each of them, they have their advantage and disadvantage. So let's say bubble sorts. What is the advantage? It's the simplicity, because it just consists of few lines of codes. Then you can arrange the sorting. So if we look at the bubble sorts here, if we compare to the merge sorts and the quick sorts, this is just only the bubble sorts. 3 lines, then you can actually done with the sorting. So as simple as that. But is it good? So the disadvantage is, if let's say you have a large sets of numbers, So probably it's not good. Why? Because it will give you the worst case of O(n) squared in terms of the time. It will take longer time to process because it has to go through every single of the elements in the array. So that's why the worst case is O(n) squared. So that is the disadvantage. So normally all the algorithms that people are actually working on is they are not going to use buffer sorts. So buffer sorts basically is just to let you understand. Next, we go to the insertion sort. So insertion sort, the advantage is that if it ends fast, when the array is nearly sorted, it's going to end fast when it's nearly sorted, and also its simplicity. Few lines of codes, right? If we look back into the insertion sort here, so it's just only few lines of codes, but the best case is O(n). So the worst case is O(n) squared. So that is the problems with the insertion sort, where also same thing if you have a large set of numbers. So probably if you have large sets of numbers, it's not suitable to use bubble sorts or insertion sorts. Merge sorts, okay, it's more efficient if compared to the rest, where it is actually O(n) log n. O(n) log n means that it used less time to process the whole array. So efficient when dealing with large amount of data, because when you have large amount of data, that it will divide it into, okay, it's going to divide it into few levels. Okay, it's divided into few levels, then it will combine it. Okay, so somebody is actually drawing okay, so for merge sorts, it's not possible that it's actually O(n) squared. It will actually remain in O because it divides into few levels, then it's starting to combine. So it's actually unlikely that it's going to be O(n) squared. It's not space efficient. Okay, it's not space efficient to store auxiliary arrays. So what does it mean? It means that if let's say so somebody is actually drawing, keep drawing. Okay, so now, so let's say it is not space efficient to store auxiliary array. So if let's say merge sort, if you're not just using the array, if you are doing it with linked list, so probably it would be more efficient to compare. Okay, it's actually more efficient to compare if you are using the linked list. So merge sorts, it is actually efficient if they are actually using a large amount of data. So here if we're looking at the quick sort, so quick sort is the fast sorting desired. So it's actually able to achieve O(n) log n. Okay, the disadvantage, okay, it would be wasted when the array is nearly sorted. If it's nearly sorted means that, you know, you have to go through every single again. So which means there's no point. So if let's say the pivot that you pick is actually largest or smallest, so that will contribute into the worst case where it's the O(n) squared. Basically, okay, to make a conclusion, okay, at the end, there is no worst or the best. It's just that you need to understand on the structure of your data. So if you know that your data is actually nearly sorted, so what you can do, you can just use the insertion sort, or you can just use the quick sort. If you know that your data is actually large, then it's better that you prefer to go to the merge sort, because merge sorts will actually reduce the time complexity of the pieces. So this is how, okay, so this is how the sorting is actually done. Okay, open F7. I guess you can actually stop drawing because that is the end of our workshop for today for the advanced level. Okay, the slides and also the codes will be shared to you. So if you're interested in how each sorting is actually working, that you want to go step by step, you can go to this Python tutor, okay, that you can actually go through each of the lines and then, to check on how does what is the mechanisms inside, true mechanisms inside, go to line by line. Okay, so that's the end of the workshop. For the whole part of the data structures, remember, before you're actually working in any algorithms, we don't care whether is it like the deep learnings or any other machine learnings. First thing that you need to look into is your data. Okay, you need to check what is the patterns of the data, then you apply the best algorithms to process your data, because the examples that we show over here, the data is only figures, right? Probably later in the future, you can deal with the images, you're going to deal with the 3D coordinates data or any other data that's more complex. So that time is not just as simple as, do sorting or searching, all that. Is more than that. But anyhow, come back to the most basic one. You still need to look at the patterns of the data and apply the most appropriate algorithms. All right, so any questions for this? Is there any questions? Okay, no questions. So for those who are actually interested in joining the test, so probably you can just go back, because I think the link will start to open at 12:30. So if there's no questions, I think that's all for today. So I wish everyone, okay, good luck. If that you're able to join the preliminary test, so good luck in your preliminary test. And then I think that's all. Okay, thank you. Goodbye.